Okay, let's take a look at number 105G. And in 105, we have integrals where to use any of the techniques we've learned. So we could be using, simple substitution. We could be using integration by parts. We could be using trigonometric substitution. Could be a, trig integral. Could be using partial fraction decomposition, and so on. Okay. Now this one, if I take a look at it, what method would I use? Well, I've got a theta times a sine inverse theta. So I'm thinking when I'm looking at a product of functions, immediately integration by parts pops into my head, right? So you got a product of u times dv, and hopefully in a way to get a simpler integral that we can do, because I have no idea what the antiderivative of theta times sine inverse of theta is. So what am I going to choose for my u? Well, remember our Liate, and log for L, I is inverse trig, and I do have an inverse trig, right? This is the arcsine or inverse sine function. So that's what I'm going to choose u to be, arcsine. dv is everything else, theta d theta. I differentiate here. The derivative of the inverse sine function, if you remember, is 1 divided by the square root of 1 minus theta squared. So du is this. Integrate theta, I get 1/2 theta squared by the power rule. So that's what v is. So my uv is sine inverse theta times 1/2 theta squared, or 1/2 theta squared sine inverse theta. There's that part. Minus v du. So v times du. So I pull that 1/2 out. Integral of theta squared over the square root of 1 minus theta squared. Okay. So notice, did the integral get easier from what we started from? I would say yes, because we don't have any inverse trig function anymore. That's one good thing about integration by parts. When we do that derivative, there's no inverse trig function involved. However, it's not just a simple substitution. If I let u be not the same u here. Now, if I let w, let's say w be 1 minus theta squared, dw would be 2 theta, negative 2 theta d theta, and I have a theta squared. And so it's a little bit tricky there. Now you could, yeah, it's just tricky there, because you got that extra theta floating around. Even though you could solve, if w is 1 minus theta squared, you can say theta squared is 1 minus w, but you still have that extra theta d theta that you need to deal with. So just substitution is not going to work. So, well, if you've been looking here, trig substitution, right? That's the way to go, right? I've got 1 minus theta squared. Notice usually we start with an integral involving x, and then we say let x equal a, in this case, what, sine, right? X equal a sine theta. But here we're going to have theta equal a sine x, because we're starting with the variable theta here. So I'm going to go back to x, because I haven't used x previously. I've done the u and the v from the integration by parts. So I'm going to do this way. Notice the value of a squared is 1, so a is 1. So let theta be sine of x, d theta is cosine of x dx, and this square root of 1 minus theta squared would be square root of 1 minus sine squared x, which is, of course, cosine squared x by the Pythagorean identity, and we get the square root of that being, of course, cosine x. So now I've substituted in. I'm just going to look at this integral here and then evaluate it, and then I'll plug it back into all of this. So here we have theta squared is sine squared x. D theta was what? Cosine dx. And then the square root of 1 minus theta squared is cosine of x. Okay. Simplify, obviously the cosines cancel. I'm just left with sine squared x. And this is one that we know how to do from the trig integrals. I mean, we've got integration by parts, trig substitution, and then we get this trig integral. And I'm going to use this, right, Pythagorean, not Pythagorean, sorry, this power reduction trig identity. All right, I'm going to use that. Sine squared is equal to 1 minus cosine of 2x divided by 2, or 1/2 times 1 minus cosine 2x. And that's what I've done here. Pull the 1/2 out. The antiderivative of 1 is x, right? So with respect to x, antiderivative of cosine 2x, that's a little u substitution. Let u be 2x, so du is 2 dx. I got a 1/2 du is dx. So it's 1/2 sine of u, where u is 2x. I can do that substitution in my head pretty much. Okay, and then plus our c. So there's the antiderivative of that. Now, to go back to the original variable theta, right? Because we're going to go back to theta. Remember this relationship here. Sine of 2x, I use another trig identity that says sine of 2x is 2 times sine of x cosine of x. All right, and 1/2 times 2 is 1. Distribute this 1/2 through, I get 1/2 x minus 1/2 sine of x cosine x plus a constant. Now the x, since theta is sine of x, x is sine inverse of theta, right? If theta is sine of x, then x is sine inverse of theta. So x is sine inverse of theta. Sine of theta, we already know, is equal to x. So sine of x, rather, is equal to theta. Cosine of x, well, you can see right here that cosine of x is equal to the square root of 1 minus theta squared. Okay, you could also do your right triangle and define sine of x and cosine of x. But there I plug it in and I get this is my answer. Now I go back to the original. Here's what I was wanting to get, right? Here's my original antiderivative of the original, right? After using integration by parts, I got to here. So I'm going to simply plug in the results that I got for the trig substitution. I need to multiply by -1/2 though. -1/2 times what I got. So I got the 1/2 theta squared sine inverse theta. Just recopy that down here. And then remember, I need to multiply -1/2 through this. So -1/2 times 1/2 sine inverse theta is -1/4 sine inverse theta. And then remember, -1/2 times what? -1/2. Negative times negative is +1/4 theta square root of 1 minus theta squared plus c. And there is our antiderivative. So you can see that one involved integration by parts, trig substitution, simple substitution, a trig integral, and just a little bit of everything. And that is really fun and exciting, at least to me it is. So again, this one's a little more challenging than some of the ones in number 105, but give those a try and see if you can put together all the ideas that we've learned. Okay, hope this helps on getting you going with these type of problems.